All right, well, let's take a look at Chapter 15, Sampling Distributions. In Chapter 15, we cover parameters and statistics, statistical estimation and the law of large numbers, sampling distributions, the sampling distribution of X-bar, the central limit theorem, and sampling distributions and statistical significance. Parameters and statistics. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. A parameter is a number that describes the population. In practice, the value of a parameter is not known because we can rarely examine the entire population. A statistic is a number that can be computed from a sample, from the sample data without making use of any unknown parameters. In practice, we often use statistics to estimate an unknown parameter. So, parameter is a number that describes the population. A statistic is a number that can be computed from the sample data. So often we hook the P in population to the P in parameter, and we hook the S in sample to the S in statistic. Remember S and P. S comes from S in statistic comes from S in sample, and P in parameter comes from P in population. S and P. We write mu, the Greek letter mu, for mean of the population, and sigma for the standard deviation of the population. We write X bar for the mean of the sample and S for the standard deviation of the sample. Again, I remind myself that the S is not a Greek letter. The X is not a Greek letter. Those regular letters, they come from sample data. The Greek letters, the fancier letters, right, the mu and the sigma, they come from the population. So if you have Greek letters, you're dealing with population information, which is a parameter. If you have not Greek letters, so like our regular English letters, then you are dealing with a sample, which means your numbers are a statistic. Statistical estimation. The process of statistical inference involves using information from a sample to draw conclusions about a wider population. And as we've seen before, we have the population, which is the box here, and then inside of the population is the sample. So the sample is a subset from the population. We collect data from a representative sample, then we make an inference about the population. Different random samples yield different statistics. We need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. We can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. Therefore, we can examine its probability distribution without, I'm going to start that one all over. We can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. Therefore, we can examine its probability distribution using what we learned in earlier chapters. The law of large numbers. If X bar is rarely exactly right and varies from sample to sample, Why is it nonetheless a reasonable estimation of the population mean, mu? Here is one answer. If we keep on taking larger and larger samples, the statistic x bar is guaranteed to get closer and closer to the parameter mu. Law of large numbers. Draw observations at random from a population with finite mean mu. As the number of observations drawn increases, the mean mu of the observed values tends to get closer and closer to the mean mu of the population. Sampling distribution. The law of large numbers assures us that if we measure enough subjects, the statistic x bar will eventually get close enough to the unknown parameter mu. So the mean of the sample will become closer and closer to the mean of the population if we take larger and larger sample sizes. If we took every one of the possible samples of a certain size, calculated the sample mean for each, and graphed all of those values, we'd have a sampling distribution. The population distribution of a variable is the distribution of values of the variable among all individuals in the population. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. And note of warning, be careful. The population distribution describes the individuals that make up a population. A sampling distribution describes how a statistic variable varies in many samples from the population. So a population distribution describes the individuals that make up the population, whereas a sampling distribution describes how a statistic varies in many samples from the population. Population distributions versus sampling distributions. There are actually three distinct distributions involved when we sample repeatedly and measure a variable of interest. The first is the population distribution. The population distribution gives the values of the variable for all individuals in the population. The second is the distribution of sample data. The distribution of sample data shows the values of the variable for all the individuals in the sample. And the third is the sampling distribution. The sampling distribution shows the statistic values from all the possible samples of the same size from that population. And here we have an image of each of the three types of distributions and how they relate to each other. So population distribution, we have a parameter of 50-50, red and blue, but in certain samples, here we have 3, but there's a ... in the middle. So we have a bunch of samples, every possible sample of size 20, where we find blue and red. And then if you look at the sampling distribution, which is a distribution of the probabilities of every single one of the sample sizes, here sample size 20, then that's what looks normal. That looks normal. So the sampling distribution shows the statistic values from all the possible samples of the same size from the population. That's what looks normal. I was looking back to see if red and blue was about something, the color of a car maybe. The sampling distribution of X bar. When we choose many SRSs, simple random samples, from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. Here are the facts. Mean and standard deviation of a sample mean. Suppose that X bar is the mean of a simple random sample of size n drawn from a large population with mean mu and standard deviation sigma. Then the sampling distribution of X bar has the mean mu and the standard deviation sigma divided by root n, the square root of the sample size. We say the statistic X bar is an unbiased estimator of the parameter mu. Because its standard deviation is sigma divided by root n, the averages are less variable than individual observations, and the result of large samples are less variable than the results of small samples. Sampling distribution of a sample mean. The sampling distribution, oh, there's nothing on that slide. A sampling distribution of a sample mean. The sampling distribution of X. Maybe there's supposed to be pictures there. The central limit theorem. Most population distributions are not normal. What is the shape of a sampling distribution of sample means when the population distribution isn't normal? It is a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. Central limit theorem. Draw a simple random sample of size n from any population with mean mu and finite standard deviation sigma. The central limit theorem says that when n is large, the sampling distribution of the sampling mean X bar is approximately normal. X bar is approximately normal with mean mu and standard deviation sigma divided by the square root of the sample size. Sigma divided by root n. The central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. The central limit theorem. Oop, went too far. Okay, so we have a population with mean mu. We have a simple random sample of that population, so a subset of that population of size n. We find every possible size n SRS we can and find the mean. So say we selected 20 of these people, we're asking ourselves maybe what's their average height, right? What's their average height? And so we select 20, we find the average height, put them back. Select 20, find their average height, put them back. Select 20, find their average height, put them back. Well, combinatorics, right? Combinations can tell us how many combinations there are in our population of size 20, and we can be sure to select every one of those instances, every combination, and find the average. And what the distribution of those averages looks like then is this third image here, the bell-shaped curve. So in some of those groups of 20, we'll get we'll select every short person on the list, and we'll be having very short averages, right? But sometimes those 20 people are going to be super tall people, we're going to get higher than normal averages. But for the most part, we'll have cancellation, and we'll end up in this big, large middle group here. Oops, let me pull down my, all right. Central limit theorem example. Based on service records from the past year, the time in hours that a technician requires to complete preventative maintenance on an air conditioner follows the distribution that is strongly right skewed and whose most likely outcome are close to zero. The mean time is mu equals 1 hour and standard deviation equals 1. Your company will service an SRS of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough? The central limit theorem states that the sampling distribution of the mean time spent working on the 70 units has an X bar of 1 and a standard deviation for X bar, which is the standard deviation divided by the square root of the sample size. So the standard deviation given was sigma, which is 1, and then we're going to divide that by the square root of the 70 air conditioners. So 1 divided by square root of 70 yields 0.12. The sampling distribution of the mean time spent working is approximately normal with a mean of 1 and a standard deviation of 0.12. Since n equals 70, which is greater than 30, our standard for large. So here we would say n is large because it's greater than 30. Which means we have a normal distribution that we can use this normal distribution because we are approximately normal with a very large sample size, with a large enough sample size, right? And now we go back to some chapter 3 concept of z-score, right? The z-score. So we're asking, will 1.1 be enough? So 1.1 is our X value, right? So if you recall, the formula for z-score was X minus mu divided by the standard deviation, right? That was our chapter 3 version. In this chapter, we're looking at a z-score being our mean X bar minus the mu given in the problem divided by the standard deviation, sigma, which itself is divided by root n. Or if you like the subscript notation, we have X bar minus mu over sigma subscript X bar, because it's the standard deviation of the sample distribution. Okay, so we have 1.1 minus 1 in our numerator, just 0.1, and we divide that by the standard deviation of the sample distribution, 0.12. So 1.1 minus 1 in our numerator divided by 0.12 yields 0.83. Erase my drawings here so you can see the words. The probability that X bar is greater than 1.1 is the probability that we have a z-score greater than 0.83. When we look up the probability of the z-score of 0.83 in table A, what we get is we get the cumulative buildup here. So 0.7967 on the left of a z-score of 0.83. And so we have to subtract from 1, right? Because if we were allowed to get the whole area under the curve, we would have an area of 1. So 1 minus the 0.7967, which we got from looking in table A, right? So go to table A and look up the z-score, 0.8 on one side, and then you go to the column that lists 0, 3, so that your z-score is 0.83. Where those intersect, you'll find the 0.7967. So that's your results from table E. So subtract 0.7967 from 1, and we get that the shaded area to the right is 0.233. 0.233. If you budget 1.1 hours per unit, there's a 20% chance that the technicians will not complete the work within the budgeted time. So what's the probability? We found that probability to be 0.2033. And then in our answer, we call that a percentage of a chance. So if you budget 1.1 hours to answer in the context of the question, there's a 20% chance the technicians will not complete the work within the budgeted time. Sampling distributions and statistical significance. We have looked carefully at the sampling distribution of a sample mean. However, any statistic we can calculate from a sample will have a sampling distribution. The sampling distribution of a sample statistic is determined by the particular sample statistic we are interested in. The distribution of the population of individual values from which the sample statistic is computed, and the method by which samples are selected from the population. So the sampling distribution of a sample statistic is determined by the particular sample statistic we are interested in. The distribution of the population of individual values from which the sample statistic is computed, and the method by which samples are selected from the population. The sampling distribution allows us to determine the probability of observing any particular value from the sample statistic in another such sample from the population.